Okay, now the last thing I want to talk about today is the quantitative relationships that are given by balanced chemical equations and how we can use them in something called stoichiometry. What is usually needed is, for a particular chemical equation, the information about how much product can we expect if we start with a certain amount of reactant. Well, the law of conservation of mass can help you sort of overall. You know the mass isn't going to change. But with a balanced chemical equation, it means the reactants are completely consumed to give these products. And you need an additional piece of information if you want to know how much of one product you're going to get out of a set of reactant quantities. We do this by using what are called stoichiometrically equivalent molar ratios, and those give us the quantitative relationship between molar amounts of reactants and products in a balanced chemical equation. Let's suppose that you have a propane cigarette lighter. I hope you don't use it to light cigarettes, but if you do, the propane, let's just say it could be used for a camp stove, all right? The propane reacts in a combustion sense to give CO2 and water, just like we saw for octane. But the balanced chemical equation is different because we have C3H8 instead of C8H18, right? And this is a balanced chemical equation, but it doesn't say it's balanced. So whenever you see something like that, the first thing you do is check to see whether it's balanced, because it might not be, and it's your responsibility to find out. Okay? So 3 carbons, 3 carbons. 8 hydrogens, 8 hydrogens. 6 plus 4 is 10 oxygens, 10 oxygens. It is a balanced chemical equation. So we can use it. And what we're going to do is focus on the balancing coefficients here. And what I mean by that is if you carry out this reaction with 1 mole of propane and 5 moles of oxygen, and it goes the way it's supposed to go, you're going to get 3 moles of CO2 and 4 moles of water. That's what the equation says, and that's what will happen. Now, if you're interested in the relative quantities of reactants and products, it means 3 moles of CO2. If you get 3 moles of CO2, you're going to get 4 moles of water. Or if you want it in terms of mass, if you take 3 moles of CO2 and convert that to the mass of CO2, you can figure out the mass of water by taking 4 moles of water and converting that to mass of water and use that ratio. There are different ways that you can do this, but it is the stoichiometrically equivalent molar ratio that let us go from amounts of one substance in a reaction to amounts of another. And this can be done in any direction. 5 moles of dioxygen is stoichiometrically equivalent to 3 moles of CO2. If you start out with 5 moles of dioxygen and enough propane, you're going to make 3 moles of CO2. So here's how we use it. In combustion of propane, how many moles of dioxygen are consumed when 10 moles of water are produced? Okay. Now, what we're going to do is, this is a mole-to-mole conversion, and in this case, it uses the balanced chemical equation to get the mole ratios that are needed. Here's what it looks like. The given amount is 10 moles of water, and we want to know how many moles of oxygen we have to provide to make these 10 moles of water. What we're going to do is to set up this molar ratio. And the molar ratio in the numerator is going to have the number of moles of dioxygen because that's what you want. That's what the units of the answer need to be. And underneath, in the denominator, we're going to have the number of moles of water, because that will allow us to get rid of moles of water units and have our answer in the units that we want. So the molar ratio is taken from the balancing coefficient. So this 5 comes from that 5 right there. And this 4 comes from that 4 right there. So you get the balanced chemical equation, and then you use the coefficients to build your molar ratio that actually converts moles of one thing to moles of another. Once the arithmetic is done, the answer is it takes 12.5 moles of oxygen to make 10 moles of water. Questions on the steps? Okay. Again, it's very important that you use units. And this is the equivalent amount to the given amount that we started. Okay. Now what I want to do is to look at a more complicated case, again, so that you'll be comfortable with this. Metallic copper, for many, many years, has been obtained from copper ore by a process called roasting. Roasting just means heating it strongly in the air. Okay? And the ore frequently is copper 1 sulfide. Not always, but most of the time it is. Now, if you've ever been around one of these operations, this is called a smelting process. And I always thought, from the time I was old enough to know, that word came from the smell produced, because sulfur dioxide is not pleasant in any way. It's certainly not pleasant to smell. So this is a smelting process. We heat copper 1 sulfide with oxygen, and we make copper 1 oxide, which is a solid, plus a gas, sulfur dioxide. So, a question, how many moles of oxygen are required to roast 10 moles of copper 1 sulfide? Now we have to have the balanced chemical equation. Reactants are copper 1 sulfide and oxygen. Products are copper 1 oxide and sulfur dioxide. Here is the balanced chemical equation, and I want you to check this to be sure that it's really balanced, so you'll be in the habit of doing it. I'm going to assume that it's balanced, but I want you to prove it to yourself that it is. So we're going to do a mole of copper 1 sulfide conversion to moles of oxygen. So moles of oxygen with the coefficient has to be in the numerator of the mole ratio here, and moles of copper 1 sulfide have to be in the denominator. So again, as we saw before, here's the 3 for the oxygen, and here's the 2 for the copper 1 sulfide. So if we carry this out, moles of copper 1 sulfide cancel, and the answer is 15 moles of dioxygen. Questions? That's a mole-to-mole case. Now we could easily ask questions about, instead of giving you the number of moles of copper 1 sulfide, we could give you the mass. And then you'd have to do a mass-to-mole conversion and then the mole-to-mole conversion. Okay? So, let's see it. How many grams of sulfur dioxide are formed when 10 moles of copper 1 sulfide are roasted? Again, here's the balanced chemical equation that we had before. And what we would like to do here is make a plan. I strongly recommend that if there's more than one step to whatever you're doing, you write down a plan, kind of a roadmap, something to guide you as you go along so you won't stray off the path. All right? We're given moles, 10 moles of copper 1 sulfide. That's where we start. We want to get mass of sulfur dioxide. As you think about this, the only way you can get mass of sulfur dioxide is if you have moles of sulfur dioxide. Then you could do a mole to mass conversion and you're home free with plenty of time to watch TV. Okay? So we're going to do a mole of Cu2S to mole of SO2, and then we're going to do a mole to mass conversion on the end. Here's what it looks like. 10 moles of Cu2S times a mole over mole conversion here. We want to go 2 moles of SO2, so that's on top. And here's the 2 over here. That we use. And then 2 moles of Cu2S, that's that 2 right there. And once we're done, copper sulfide moles will disappear. Our answer at this point will be in moles of SO2, And then we do a mole to mass conversion, 64 grams of SO2, the formula mass, divided by 1 mole of SO2, gets rid of the moles of SO2, and we end up with 641 grams of SO2. So that's a mole to mass. Yes?
So are we only dividing it by 1 mole?
Yeah, this is the 32.07 plus 2 times 16, so that's 1 mole.
I know, but on the bottom, is it divided by 1 or is it divided by 10?
This is not involving the equation. It is the mole to mass process that we learned before. And that process has grams that are present in a mole, in 1 mole. Okay. Now, finally, how many kilograms of dioxygen are needed to form 2.86 kilograms of copper 2 oxide? This is the whole shebang. Mass to mole to mole to mass. Okay, you can't go directly from mass to mass, although many students try. We need to do 3 steps. We need to do kilograms of oxygen to moles of oxygen. That's this first step. I'm sorry. Kilograms of copper 1 oxide to moles of copper 1 oxide, which is what we're given right here. And then moles of copper 1 oxide to moles of oxygen, and then we'll do a mole to mass conversion to kilograms mass. Okay? So the first step will be 2.86 kilograms of copper 1 oxide times the mass to mole conversion constant here, but that's given in grams, not kilograms. So we better get rid of the kilograms. So we multiply by 1,000 grams over a kilogram in this free step here. That gets us to grams, and then we can do the mass to mole. Works nicely. 1 mole of Cu2O, here's your 1 mole again, it's 143.1 grams, and that is 2 times the mass of copper, the atomic mass of copper plus the mass of oxygen. That's where the 143 comes from. Look for it in the periodic table, and remember this is a way to determine from the mass in grams how many moles there are. So we're almost there, but not quite. 20 moles of Cu2O is how much we can create from 2.86 kilograms of Cu2O. Okay, that's the equivalent amount. So that's the first step. Next step will be go from moles of Cu2O to moles of dioxygen. This is the mole-to-mole thing like we saw in the first step here. So 20 moles from over here, Cu2O, and we want to have the number of moles of oxygen. That's because we're in the plan. Isn't it nice that we wrote a plan so we know what to put there? If we didn't write a plan, then we have to go back and think it all through, and there's a chance you might make a mistake. Write it down. You don't have to think it through again. So this is 3 moles of dioxygen in the balanced chemical equation per 2 moles of Cu2O. And once we do that, the moles of Cu2O cancel, and we get an answer of 30 moles of oxygen. Everybody with this all right so far? You could do this all in one line, but I'm taking it apart step by step to be sure that you're very comfortable with what's going on. Okay? All right? The final step is to convert moles of dioxygen to kilograms of dioxygen. So we'll do a mole to mass to grams, and then from grams to kilograms. And as you see, this is the answer, 32 grams of dioxygen. Many students make the mistake of writing a 16 right there. Oxygen doesn't come as atoms. It comes as molecules. So you have to obey the formula here. To get the formula mass, it's 2 times 16, 32 grams of oxygen per 1 mole of oxygen as a dioxygen molecule. So now we convert to kilograms, 1 kilogram over 1,000 grams, and that gives us 0.960 kilograms of of dioxygen. Do we have a question on that? Okay. Give you a chance to think. If there's no question here, I want to do one more thing where I write out the whole, let's do it this way, the whole step-by-step thing in one line. Because ultimately, that's what you need to do. You need to be able to do it all in one line. You're not going to have time to mess around breaking it up into steps. That is to keep you clear about how to write the plan. So, why does 0.1 gram of magnesium give 0.166 grams of magnesium oxide in the flashbulb reaction? The balanced chemical equation for the flashbulb reaction was 2 magnesium plus dioxygen goes to 2 magnesium oxide. Okay? So, we need a plan. We're given the mass of magnesium here. And we're asked, why does that much magnesium produce this much magnesium oxide? So I propose to you that the simplest way to do this is to do mass of Mg to moles of Mg to moles of MgO in the mole to mole to mass of MgO. If I'm right, 1/10 of a gram of Mg times 1 mole of Mg over 24.3 grams of Mg from the periodic table times, in the balanced chemical equation here, we have 2 moles of MgO over 2 moles of magnesium. That'll get us to moles of MgO. Thank you very much. And then finally, we need to do moles of MgO to mass of MgO. So that is, we look at MgO. Mg is 24.3. Oxygen is 16. So that's 40.3 grams per mole. So this is 40.3 grams of MgO per 1 mole of MgO. Anybody got a calculator? Somebody calculate it for me. Tell me what it is. 0.1 times 1 over 24.3 times 40.3. Anybody got it? 0.1. 0.166? 0.166. Okay. And this is, what are the units of this? Grams? Magnesium oxide. Well, that's what the problem asks us to check. So, all written out in one line. All you got to do is keep track of the units. Grams, magnesium cancel out. Moles of magnesium cancel out. Moles of magnesium oxide cancel out, and we get grams. Thank you very much for your attention, ladies and gentlemen. We're finished.